ME347, Example 8. A smooth sphere with a density similar to that of glass is falling in water. Equations for the volume and surface area of a sphere are given. For part A, find the terminal velocity for a sphere with a diameter of 0.1 millimeter, which is similar to a fine grain of sand. For part B, find the terminal velocity for a sphere with a diameter of 5 centimeters, which is similar to a golf ball. For part C, sketch the flow fields for parts A and B for both a smooth and rough surface, indicating how the terminal velocity would change. For this problem, we will assume steady flow over a smooth sphere. Also, that water is a Newtonian fluid with constant properties at standard temperature and pressure. Finally, that the water is quiescent and the falling sphere is far from any surrounding boundaries. We begin our analysis by drawing a free body diagram and doing a simple force balance. Note that most of the external flow problems from now on will begin this way and end with needing to calculate a drag coefficient using either a correlation or an analytically derived relationship. For our falling sphere, we define our coordinate system such that z is in the upwards direction, thus g is in the negative z direction. We then add force vectors to our diagram, where the weight acts downwards and the drag and buoyancy act upwards. Since our sphere is moving at a constant terminal velocity, the sum of the forces in the z direction is just 0. Substituting in our equation for the drag in terms of the dimensionless drag coefficient, buoyancy, which is equal to the weight of the fluid displaced, and weight, we get an equation for the terminal velocity. Now, for part A, for the very fine grain of sand, we begin by assuming that the Reynolds number will be very small for this case, which I will need to check later. Thus, I can use the drag coefficient relationship for creeping flow, which is also called Stokes flow, that can be derived analytically. Plugging this in, we get an equation for terminal velocity, indicating it increases with density difference and diameter and decreases with viscosity as expected. For our fluid properties and diameter, we get a terminal velocity of 2.4 millimeters per second. Thus, it takes a very long time for grains this size to settle. Finally, for part A, we check the Reynolds number, and it is indeed very low, and our assumption of creeping flow has been verified. Now, for part B, for the golf ball size sphere, we know that the Reynolds number will be much larger. To determine a reasonable drag coefficient to use, we are looking at a plot of drag versus Reynolds number for both a smooth sphere and a smooth cylinder. For the sphere, we see the relationship for Stokes flow at very low Reynolds number. Then, as Reynolds number increases, the drag coefficient decreases almost linearly on a log-log plot up until a Reynolds number about 1,000. Then, between 1,000 and 500,000, it stays relatively constant at 0.5. For a first calculation, it is convenient to assume that we might be in this Reynolds number range, calculate a velocity, and then check the Reynolds number at the end. If necessary, we will iterate until convergence. For this case, with a constant drag coefficient, we get a different relationship for terminal velocity. Note that we still find the velocity increases with density ratio and diameter, but not as significantly, but that it no longer depends on viscosity. This indicates that pressure drag is dominating the total drag. Substituting in our properties, we now get a much larger velocity of 0.81 meters per second. Finally, for part B, we check the Reynolds number, and it is indeed within the range we assumed, and we do not need to iterate for convergence. For this range of Reynolds numbers, the drag coefficient is approximately constant because the size of the wide turbulent wake is also constant. For part C, we draw streamlines for each case and consider how surface roughness changes both the flow field and the terminal velocity. First, for part A, for the very low Reynolds number with creeping flow, the streamlines look symmetric front to back, and the drag is due mostly to friction. Changing the surface from smooth to rough has negligible impact on the streamlines, drag, or terminal velocity because the flow still just creeps over the surface. Second, for part B, at a moderately high Reynolds number, for a smooth surface, a laminar boundary layer forms and then grows along the front side of the sphere. The boundary layer then separates from the surface of the sphere at approximately the midpoint, resulting in a wide, turbulent wake with about the same diameter as the sphere. Thus, as indicated earlier, the total drag is dominated by the pressure drag. Now, if the surface is made sufficiently rough, the boundary layer trips to turbulent. Because a turbulent boundary layer has more momentum and kinetic energy due to turbulent mixing, it stays attached to the surface longer. This delays separation until the back of the sphere and reduces the size of the wake. Again, because pressure drag dominates, even though there is a slight increase in friction drag, the total drag drops for the smaller wake. Thus, the terminal velocity will increase.